SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Hello everyone, my name is Ankur Karnsagara. I am from DKV Arts and Science College, Jamnagar. Today I am going to discuss Boolean algebra. So let we have some basic definitions of Boolean algebra. First definition is of poset, right? Now in a poset we have a relation less than or equals to and on a non-empty set X. Now if that relation satisfies reflexivity, antisymmetricity and transitivity or the elements of X, then that relation is said to be a partially ordered relation, and the pair X is said to be a less than or equals to the pair X less than or equals to is said to be a partially ordered set. Now here we have a relation less than or equals to as a reflexive, antisymmetric and transitive. Now what do you mean by reflexive? Let us see first of all that. Reflexive means, so if we take any elements from X, then A should be less than or equals to A. That means A is related to A. That is reflexivity. Antisymmetricity means A is less than or equals to B. B is less than or equals to A implies A is equals to B. And transitivity means A is related to B, B is related to C, then A should be related to C. So here any relation satisfies these three conditions, then that relation is said to be a partially ordered relation, and the pair X is less than or equals to said to be a partially ordered set. Let us take an example. In an example, suppose we have X is equals to A and B, right? Now for that A and B, power set of X is equals to set, empty set, singleton set A, singleton set B and set X itself, right? So here we have power set of X is equals to 5 singleton set A, singleton set B and X itself. Now with this power set of X, if I choose less than or equals to, that means A, B is less than or equals to B if and only if A subset or equals to B. Okay, so here we have A subset or equals to B, right? Now with this relation A subset or equals to B, power set of X is a poset. Now let us see how. If we take any X from power set of X, then X is subset or equals to X, that we can see. Therefore subset or equals to is a reflexive. Now for two elements X is less X and Y from power set of X, then X, and if we have X is subset or equals to Y, Y is subset or equals to X, then this implies we know that X should be Y, and this is an easy exercise of set theory. Now and the third condition is that if we have elements A, B and C from power set of X, and the condition is that A should be subset or equals to B, B should subset or equals to C, and that implies A is a subset of C. Again, this is an easy exercise of set theory. So here we can see that less than or equals to is equals to, that means subset or equals to is a reflexive, antisymmetric and transitive. Therefore power set of X with subset or equals to is a poset. So this is the definition of poset. Now let us see the next definition on the PPT, that is cover of an element. So cover of an element. Here we need a poset P less than or equals to. Now any two distinct elements, for any two distinct elements A and B, B is said to be a cover of A if A is less than or equals to B, and there is no C in set P such that A is less than or equals to C and C is less than or equals to B. Please keep in mind that here less than or equals to is not a usual less than or equals to. Less than or equals to means A is related to B, A is related to C, C is related to B. So this definition says that there is no element between A and B such that A divides C, A related to C and C related to B. Now in our example power set of X, let us see how any element is a cover of B. Here we can say that in a power set of X, subset or equals to singleton set A is cover of phi, because there is no element C in power set of X such that empty set is a subset of C and C is a subset of singleton set A. Similarly, here singleton set B is again a cover of phi, because there is no element C in a power set of X such that phi is subset of C and C is a subset of singleton set B. So here in a power set of X with X is equals to A and B, there are two elements as a cover of phi. There are elements singleton set A and singleton set B. So this example says that it may happen that some elements have two or more than two covers, right? And it may happen that there is no cover of an element. Now let us see the next definition. Next definition is greatest lower bound. In short, will denote as a GLB. Now in that we again need a poset. So let us take a poset X less than or equals to and take any set a subset of X. Now if there exists Z in X such that Z is lower bound of A, that means Z is less than or equals to each and every element of A. And second condition is that if we have any another lower bound Y, then Y is less than or equals to Z. Then Z is said to be a greatest lower bound. Again, here less than or equals to is not a usual less than or equals to. It is related, right? So this definition says that any element can be a lower bound of a subset of any set. For example, in a power set of X, here we can say that phi is the lower bound of any set A subset or equals to power set of X, right? Any set power set of X, and there is no other lower bound such that phi is a subset of A. Therefore phi is GLB of any set A, right? So here phi is nothing but GLB of set A. Similarly, the next definition says that least upper bound. Now in a least upper bound, what we have, this definition is similar to a greatest lower bound, but it will be in another form. That means it is in a upper bound form. So here again we take a poset X less than or equals to E and a subset A of X. Now any element Z in X is said to be a upper bound of A if X is less than or equals to Z for every X in A, and there exists any other bound, any another bound, upper bound Y of A, then Y should be greater than or equals to Z. That means Z is a least among all upper bounds of set A. Then that's Z is said to be a least upper bound of set A. So here in a power set example, power set of X less than or equals to, again X is upper bound of A subset or equals to X. That means A is an element of power set of X, and X, if we take any other upper bound, then X is a greater one. That means X is a most one than upper bound. So here X is said to be a least upper bound of set X, and phi is said to be a GLB, greatest lower bound of power set of X, or you can say that any subset A of power set of X. So here this is the concept of GLB and LUB. Now next is lattice. For a basic definitions, here lattice is that take any poset L comma less than or equals to, and for any two elements X and Y from that set, GLB of that two elements and LUB of that two elements should exist in the poset L. Then L comma less than or equals to said to be a lattice. So here we need GLB and LUB of two elements X and Y in a set L, right? Whenever we have this condition, then that poset is said to be a lattice. Here we need some notations for GLB of X and Y and LUB of X and Y. The notations are that X star Y is equals to GLB of XY, and X ring sum Y is equals to LUB of X and Y. Now with these notations, star and ring sum, we have some properties like this star is a commutative. That means for two elements X and Y, X star Y is same as Y star X. Similarly for ring sum, x ring sum y is same as y ring sum. So here we have star and ring sum as a commutative operators. Similarly, star and ring sum are associative. Associative means x star y star z is equals to x star y star z, and same terminology will follow for ring sum. Also, this star and ring sum satisfy absorption law. Now let us see what is absorption law. Absorption law says that for two elements x, y, z, three elements from lattice L, then x star x ring sum y is equals to x, and z ring sum x star so x star z, it is again a z. So here this law is said to be absorption law. Now in the second part, that is in x star z, we need a star is a commutative. Therefore here we can write down z ring sum z star x is equals to z. This law is said to be an absorption law. It is an easy exercise to show that again defined star and ring sum as above both satisfy this absorption law. Now next definition is bounded lattice. Bounded lattice is a lattice in which GLB of whole set and LUB of whole set exist, right? We need these two definitions, these two conditions for whole set. In a lattice we have GLB and LUB of two distinct elements, two elements only, but here we need GLB and LUB of whole set. And again let us take an example. That example is of power set of x, again less than or equals to with x is equals to set A and B. Now this power set of x is an bounded lattice because we know that phi is GLB of power set of x and whole x is LUB of power set of x. That means for whole set L is equals to power set of x, phi and x are GLB and LUB of power set of x respectively. So power set of x with less than or equals to is bounded lattice. Now in the next we have notation for the GLB of L and LUB of L as a GLB of L is equals to 0 and LUB of L is equals to 1. Here 0 and 1 are not usual 0 and 1. They are the 0 elements. 0 elements says that GLB of L and 1 element says that LUB of L. Now the next definition is basic definition, complemented lattice. Complemented lattice, for that we need a bounded lattice. Now that lattice is said to be a complemented lattice if for any element A there should be at least one element B in L such that A star B is equals to 0 and A ring sum B is equals to 1. Here let me clear that 0 is not usual, 0 and 1 is not usual. 0 means GLB of lattice L and 1 is LUB of lattice L. So for complemented lattice we need a bounded lattice because we need 0 and 1. So here definition says that A star B is equals to 0 means GLB of A and B is 0 and LUB of A and B is 1. For example, here in a power set of X, 0 element is a phi and X is 1 element, right? Now take two elements, singleton set A and singleton set B. Now here I will show that singleton set B is a complement of singleton set A. Now for that what we need to prove? Our claim is to prove that singleton star set A star singleton set B should be 0, that is phi, and singleton set A ring sum singleton set B should be X. Now here star and ring sum for power set of X, that means greatest lower bound of singleton set A and singleton set B. Now in a power set of A, greatest lower bound is given by a intersection and least upper bound is given by union. So here A star B singleton set A star singleton set B is same as singleton B is same as singleton A intersection singleton set B. Now here there is no element common to both, therefore this intersection will be phi and singleton set A ring sum singleton set B is equals to singleton set A union singleton set B. Now union of these two elements will be set AB, and that is our X. Therefore, for two elements singleton set A and singleton set B, its star is 0 element, this phi is 0 element, and ring sum is X, that is 1 element. So 0 element and 1 element. So complement of A is B. Now here we can say that singleton set, since star is a commutative, singleton set A star B is same as singleton set B star singleton set A. Therefore complement of B is complement of A. So here complement of A is B and complement of B is A. This is one example. Another example is that phi is the complement of X, the whole set X. Phi is the complement of whole set X. Now let us see how it's possible. Here we know that phi star X is equals to phi intersection as X, because in a power set of X, star means intersection, and both intersection will be phi, and phi ring sum X is equals to phi union X, that is equals to whole set X. So here we have both elements, star is equals to empty set, that is 0 element, and both ring sum is X, that is 1 element. So phi is a complement of X, and similarly X is a complement of phi. So this is about a complement of any elements in a set. Now complemented lattice says that for each and every element of that set, there should be a complement of that element in a given set. Here we have 4 elements that are phi X singleton set A singleton set B in a power set of X. Now phi is a complement of X, X is a complement of phi, singleton set A is a complement of B, and singleton